Once we know that a polynomial has a real root somewhere, we want to know where to start to look for it. Our first pass is going to be to establish upper and lower bounds on the zeros. Remember, we had a method of doing that using synthetic division. And often we'll be lucky enough to establish bounds on the roots in the process of showing that the polynomial has no rational roots. We want to try for rational roots first, because those are going to work better. So let's see an example, and we'll see what this looks like. Here we have a polynomial, x to the fourth minus 4x minus 3. We want to show that it has no rational roots, and we also want to get an upper and lower bound on the roots. Now, to see that it definitely has some real roots, we see that this polynomial has one sign change. So it has one positive root. If we plug in negative x, well, we've got x to the fourth plus 4x, right? That's an odd power of x, minus 3. That also has one sign change. So we have one negative root. We know we have two real roots, one positive and one negative. The possible rational roots, our constant term is 3, our leading coefficient is 1. So our possible rational roots are plus or minus 1, plus or minus 3. There's only 4 possibilities. We can just do all of that synthetic division. Now, if we just wanted to show that these are not roots, we could absolutely just plug these numbers in on the calculator. However, we also want to see if we can establish an upper and lower bound. And for that, we need to actually see the synthetic division. So let's do that. Bring down the 1, times 1 is 1, plus 0 is 1, times 1 is 1, plus 0 is 1, times 1 is 1, minus 4 is negative 3, times 1 is negative 3, minus 3 is negative 6. Not 0, and because we have a positive number and a negative number here, this is not an upper bound. Now we'll try negative 1. Bring down the 1, times negative 1 is negative 1, plus 0 is negative 1. Times negative 1 is positive 1, plus 0 is positive 1. Times negative 1 is negative 1, plus negative 4 is negative 5. Times negative 1 is positive 5, minus 3 is positive 2. So that's not a 0, but notice these signs alternate, and this is negative. So this is a lower bound. There are no roots less than negative 1, which means 1, we've already established a lower bound on our roots, and 2, we don't have to try negative 3. Okay, that means all that's left to do is to try 3. So bring down the 1, times 3 is 3, plus 0 is 3. Times 3 is 9, plus 0 is 9. Times 3 is 27, minus 4 is 23. Times 3 is 69, minus 3 is 66. So here we see these are all positive, and this is positive. This is an upper bound. Three is an upper bound. So we've established 3 facts now. We've established that there are 2 real roots, one positive and one negative. We've established that there are no rational roots. And we've established that both roots are between -1 and 3. That's pretty good. We know that there are two roots, one positive, one negative. They're both irrational, and they're both between -1 and 3. We have a fairly straightforward way to be a little bit more specific about where they are. And that is to say what two consecutive integers our 0 is between. So they're both between -1 and 3. But are they between 1 and 2, or between 2 and 3, or between 0 and 1? That's the question we want to address. For a lot of applications, that's actually good enough, because we only want the closest possible integer. And that's also pretty easy to get just from an arithmetic standpoint. So now that we know that our roots are between -1 and 3, the easiest way to find what consecutive integers they're between is to just make a little table. So our x value can be anything between -1 and 3. We're going to fill in the corresponding y values, and the easiest way to do that is to get our calculator to help us. So I'm going to grab my calculator. I'm going to go to Table and enter my function, which was x to the 4th minus 4x minus 3. And I'm going to say I want to start at -1 and just count by ones and say OK. So I see that when x is -1, y is 2. When x is 0, y is -3. When x is 1, y is -6. When x is 2, y is 5. When x is 3, y is 66. So what do we see in this table? Y goes from positive to negative here. So our -0 is between -1 and 0. It goes from negative to positive here. So our +0 is going to be between 1 and 2. So we've now narrowed down what two consecutive integers our zeros are between. For many applications, that's going to be good enough. For some, though, we'll want to get a better estimate, and we'll see how to do that in the next video.